11.9, total internal reflection. So this time let's take the ray going from glass into air. Now this time it's going to bend away from the normal, isn't it? Look, here comes our wavefront. This time this end exits the glass into air and speeds up before this end of the wavefront. So we get this. Boom. Whoop. Oh no, sorry, let's do it again. Here we go. Whoa, there we go. Okay, so we did that, don't we? This end speeds up first. So we could use Snell's law to work out what the angle of refraction is here, because we know the two refractive indices. Look, I've swapped them around. Glass is up here, air is down here. The incident angle is 40 degrees. You stop the video and work out the angle of refraction, and I'll tell you at the end what the answer is. Exciting. Anyway, total internal reflection. What's that about? If we increased this angle of incidence, because the angle of refraction is greater than the angle of incidence, the angle of refraction is going to reach 90 degrees before we get the angle of incidence to 90 degrees, isn't it? Yeah, that ray will hit the boundary before this ray runs out of glass, as it were, right? Well, what happens at that point? Well, total internal reflection. The ray will no longer refract out of the glass into the air. It will reflect off the inner surface of the glass back into the glass, and it'll then obey the angle of reflection. The angle of reflection is equal to the angle of incidence. Okay. Now, there's a special angle where that just starts to occur, where if you increase the angle of incidence any more, you get total internal reflection. In other words, this special angle, the critical angle it's called, is when the angle of refraction is 90 degrees. And let's work it out for this scenario here. Okay. So let's put our numbers in. I'm going to rearrange the equation for sine theta 1. That's what we want to know. So theta 2 will be a right angle, and these are the refractive indices we need to work with. So I've rearranged the equation. Sine theta 1 equals n2 sine theta 2 divided by n1. Move it down there. Put our numbers in. Here we go. Refractive n2. Yeah, n2 this time. What the second material is air. Refractive index 1.00. Sine 90, which you'll know is equal to 1. Actually, so all of this top part of the fraction, the numerator becomes 1 divided by 1.42, and 1 up there. Okay, which gives us 0.7042. Inverse sine of that gives us 44.8 degrees to 3 sig figs. Now, because this top part of the equation goes to 1, we can simplify the Snell's law equation for the critical angle. The symbol for the critical angle is a capital C, not to be confused with the symbol for speed of light in a vacuum, which is a lowercase c. Okay, so it's just 1 over n, where c is the critical angle, n is the refractive index of the material that the light is coming out of. Okay, that's it. That's all we need to know. So do lots of work now, because it's the last bit of work I'll be asking you to do before the summer holidays. So you can do notes, please, from pages 211 to 215, 11.8 and 11.9. Do the questions on page 212. Do the optical fibres questions on page 215, and then the summary questions on that page as well. And then do the end of chapter practice questions. There are 8 of them. They're past paper questions, so they give you a bit more exercise than the summary questions do. All right. And down at the bottom here, here's the answer to the question above. This time I used n sine theta equals k, work out k, use k for the second case, and then work out your angle of incidence, which was 66 degrees. Okay. Is that the angle of incidence? No, hold on. Sorry, it's not the angle of incidence. What the question was what's the angle of refraction? That's right. So yeah, before we got on to talking about the critical angle. Okay, fine. You probably know what we're doing. Yeah, I wanted to just know what R is easy. So anyway, 66 degrees, it looks right, doesn't it? It's going to be more than 40, about a third more. All right, well, even more than a third more, actually. Once we get back into, at some point, we'll start to use, I'll be able to demo things to you in September, and we won't be able to do class experiments in September, but I'll be able to demo things, and I can show you. I can show you all of this experimentally. All right. I hope you're all well, and see you soon. Bye.